Hello everyone, I'm Professor Xiaonan Gao. Welcome to the General Chemistry class. This session will finish the thermochemistry chapter. Last class, we learned the enthalpy and internal energy changes in a chemical reaction. The measured enthalpy change for a reaction has a unique value only if the initial state, the reactants, and the final state, the products, are precisely described. If we define a particular state as standard for the reactants and products, we can then say that the standard enthalpy change is the enthalpy change in a reaction in which the reactants and products are in their standard states. This so-called standard enthalpy of reaction is a key part of this session. To be specific, the question we encounter in chemistry study is that since there's no way to measure the absolute value of enthalpy of a substance, must I measure the enthalpy change for every reaction of interest? Of course not. Chemist has established an arbitrary scale with a standard enthalpy of formation as a reference point for all the enthalpy expressions. This standard enthalpy of formation, delta H standard formation, is a heat change that results when 1 mole of compound is formed from its elements at a pressure of 1 atmosphere. According to the definition, this standard enthalpy of formation of any elements in its most stable form is 0. Then how about the other elemental form of the substances? Oxygen gas is more stable than ozone. Therefore, the standard enthalpy of formation for oxygen gas is 0. But the standard enthalpy of formation for ozone is 142 kilojoules per mole. Similarly, graphite is the most stable form for carbon. So the standard enthalpy of formation for graphite is 0. And the diamond's standard enthalpy of formation is 1.9 kilojoules per mole. Here's a table listing standard enthalpy of formation for some of inorganic substances at 25 degrees Celsius. For allotropes, we can find that their most stable form in the table, like carbon, like oxygen, like sulfur. With the standard enthalpy of formation, it's a very powerful tool for calculating the standard enthalpy of reactions. The standard enthalpy of reaction is the enthalpy of a reaction carried out at 1 atmosphere pressure. Take the following chemical equations for example. A moles of A react with B mole of B to produce C mole of C and D mole of D. The standard enthalpy of reaction is to use the sum of the standard enthalpy of formation of the products times its corresponding coefficients minus the standard enthalpy of formation of the reactants times its corresponding coefficients. However, sometimes we cannot directly determine the change of delta H in some reactions. For example, when carbon burns not completely in air, it produces both carbon dioxide and carbon monoxide. But how can we get the standard enthalpy of reactions for carbon reacts with oxygen to produce only carbon monoxide? For this purpose, Hess's law was found to solve the problem. Enthalpy is not a state function. It doesn't matter how you get there, only where you start and where you end. So the Hess's law is that when reactants are converted to products, the change in enthalpy is the same whether reactions take place in one step or in a series of steps. From reactant A to product D, the enthalpy change has been fixed. No matter you go directly from A to D or experiencing two interstate mediate B and C, the sum of the delta H1 plus 2 plus 3 equals the delta H. For calculating the standard enthalpy of reaction for the production of pure carbon monoxide, let's apply the Hess's law with this scheme. From carbon to carbon dioxide, the enthalpy change has been fixed, no matter it goes directly from carbon to carbon dioxide or two processes with the carbon monoxide as an intermediate. Therefore, the delta H bottom equals the addition of the two delta H as a top. Since it's very easy to measure the enthalpy of reaction for producing pure carbon dioxide, either from the combustion of carbon or carbon monoxide, we can get the delta H by subtracting this delta from the whole delta H. Now let's use a practical example for further understanding the Hess's law, calculating the standard enthalpy of formation for carbon disulfide giving the three equations. For the first step, we need to write the equation for the formation of carbon disulfide. One graphite carbon reacts with two rhombic sulfurs to produce the carbon disulfide. For the second step, add the given reactions so that the result is desired reaction. One carbon, two sulfurs, double reaction 2. So double reaction 2. And reverse reaction 3 to get the carbon disulfide. Don't forget to reverse the sign of delta H in equation 3 from negative to positive. 3 oxygen gases cancelled. 1, 2, 3. 1 carbon dioxide cancelled. 2 sulfur dioxide cancelled. So the leftover is what exactly we need for the formation of carbon disulfide. Therefore, the enthalpy of standard formation of carbon disulfide is 86 kilojoules per mole after adding them together. By the end of chapter, the last key term is the enthalpy of solution. The enthalpy of solution is the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. We can write it down as delta H solution equals H solution minus H component. The enthalpy of solution is actually very useful. Let's take a look at this table for the heats of solution of some ionic compounds. Some delta H solution is negative, but some of them are positive. So which substance could be used for melting ice and which substance could be used for cold pack? For melting ice, we need the substance to release a lot of heat when dissolving. Therefore, potassium chloride is an optimal candidate since its delta H value is high and it is not smelly. For cold pack, we need the substance to absorb a lot of heat when dissolving. So calcium chloride is the optimal choice for its high negative delta H solution and cheap price. Alright everyone, in this session we learned the standard enthalpy of reactions, formations, solutions, and Hess's law for calculating indirect delta H. I hope you have enjoyed the class and I'll see you next time.